Assalamu alaikum wa rahmatullahi wa barakatuh. In this handout, they give a list of derivations for things like Reynolds number, pressure coefficient, velocity. But what do we actually need in our results section? Well, the bare minimum are these three things. They want to see a calculation for the tunnel calibration constant. Then they want to see a graph with pressure coefficient on one axis and angle on the other axis, and they want to see three lines on it. One line for our smooth flow, one line for our turbulent flow, and one line with this equation, which is for frictionless flow. Then after that, they want to see an estimation of drag coefficient. How that's done is basically, that's just another graph, and we work out the area under it, and we basically half it. So we'll go over that. So to start off with, we have to look at their derivation for a bit. They start with Bernoulli. Obviously from last year, this is the relationship along a streamline. So that's at one point and another point, the pressure, the hydrostatic pressure, the kinetic, the dynamic pressure at one point is equal to the same stuff at the other point. So they've worked through that, just like the report from last year. And at this point, that's where it's a little bit difficult to understand. Why is P1 this? Why is P infinity that? And in fact, what is P infinity? What is P1? And what are these terms here? So to define those terms, P1 is the stagnation pressure. So this is our wind tunnel. The air is coming in from this direction. The air has a velocity V infinity, and the air incoming, the free stream, the pressure of that air is P infinity. When it comes into contact with this body, the V at that point, velocity at that point, becomes zero, and a stagnation point is formed. And in our case, that occurs at the angle theta equals 0, and that's P1. P1 is that equation that they had over there because of this right here. Simple manometer stuff. So P1 right there, if you connect a manometer to this point, it's going to show you a height. So it's going to show you something inches, just like we measured. Okay? And from that height, you can use that to work out what P1 is. That's what you would do here. So imagine we were standing there, looking at it from this side, and we could see H1 going up and down, depending on the speed or whatever. So if you want to work out P1, then this manometer has another side connected to the atmosphere. And if you start from atmospheric pressure, you can work out P1. So P1 equals pressure of the atmosphere plus rho GH, rho G delta H, rho of this fluid, G delta H, add that to P atmosphere and you get P1. What is HA? What is H1? H1 is the side we could see for this particular point. So the manometer at that point is it's showing pressure. We can work out pressure P1, and it is showing us the height H1. The other side, we couldn't see this side. It's connected to the atmosphere, and that height, let's call it HA. Okay, we don't need it we don't need HA in the next step because it cancels out and it goes. But just to understand it, HA minus H1, and you get delta H, which is what we basically need. The difference between that picture and our one is that it's inclined at an angle of beta. So since it's inclined, we can't use just delta H. We have to use delta H sine beta to get that height, and that's why that is what it is. The same thing happens here for atmospheric pressure, free stream pressure, P infinity, which is this point right here. The same thing happens. No, it's focused. Okay, so you can start from atmosphere plus rho G delta H, H1 minus H infinity. If you were wondering why their one has a minus and why it's swapped around, well, it's basically the same thing. They had a minus there, but they swapped these two around. If you don't swap them around, you can keep the plus. It's exactly the same thing. And sign B at the end because of this, and that's why these two are what they are. That should be a infinity sign, not P2, P infinity. Right, the next thing. In their derivation, they've showed us velocity. This is just an equation for working out velocity. We can use all these terms that we know. Rho ms is the manometer's fluid density. Rho air is air density. Even though in those 3 points that they wanted as a bare minimum, it didn't say velocity in them. But the example guy's coursework, he had some velocity in it or something. I don't know why it's there, but to be honest, you don't really need this. What you actually do need is to work out K, which they've explicitly said. And to work out K, they've given us an equation on this side. So that's the next thing we need to do after we have sorted out our data results. So how to sort out the data first of all. From the experiment, we ended up with these kind of readings. These things. What you have to do is put them into one Excel sheet, and the order they go in is like this. There's 0 there. There's 10. On the next page, there's 20. Okay, and then you go back to the first page, there's 30 on this one. So put all of that in one column in Excel. So have a look at this one here. So these are our readings that we got from them, from the experiment basically. Theta there and the manometer height that we read over there. The first thing we have to do before we do anything, we have to convert it into the appropriate units. So that can't remain how it is. It has to become from inches into meters. You have to do that for each point. For all of those theta values, we got a h. And for all of them, you need to work out the h in meters. And that's simple in Excel. You just times it by 0.024. Yeah, so I just did that times 0.024 and I got them all in meters. Okay, so that's done. T atmosphere, we measured it in Celsius, make it Kelvin. P atmosphere, measured it in millimeters mercury, that needs to become pascals. We need these two for this basically. We need to work out the density of the air in our conditions. Density of the air, you can find it on Wikipedia, but we have to use our temperature that we measured and our pressure that we measured and work it out using this formula here. P atmosphere over specific gas constant for dry air times temperature atmospheric, and this is what I got from my one. So my rho air is this, everyone's rho ms is that, because they gave it to us. What else? Convert this, and also convert this. This is Betz manometer. So that one with that dial on it that we were turning, and then we had to keep it at 15 and we had to keep it at 35. That is in millimeters H2O. We need to make that into meters basically, which is simple. So after all of that has been converted, then we can go on to the first step, like we said. So I don't know why we're doing this, but that one they've said they definitely want to see. So how to do each one? You have to do it for smooth flow. You have to also do it for turbulent flow. So for smooth flow, how do you do this? You work out rho air, like we did over there. H1 for my measurements. H1, remember, what was it? H1 was where theta is 0. H1 is the height measured at theta is 0. And I got 0.307, this thing. H infinity is tube 34. So H infinity is tube 34. And tube 34 is basically, if you look at the picture here, tube 34 is basically not connected to this, it's connected somewhere upstream. And it's basically telling you the same thing as the Betz manometer is telling you. It's another instrument for measuring the same thing. So to work out velocity, simply plug in the stuff here and you can work out velocity. So for example, my one, V infinity, was this by using that. And I did that for smooth flow and for turbulent flow. Haven't decided what to do with it though in my report, if I put it in or not. I probably will, but I don't know. I'll look at the example guide. Okay, next thing, K. K they definitely want. They've said they want it. This same thing, you plug in the numbers into here. The equation is given. Density of water is 1000. Betz manometer, we converted it. These we converted it as well. And sine B is sine B. And I got that for my smooth flow. And I got this for my turbulent flow. So that's simple so far. We've worked out K. That's the first thing that they wanted in their little list of stuff we want to see. Where's it gone? Those 3 points. That right there. Okay, tunnel calibration constant. That's the K. Next thing they want to see is pressure coefficient against theta. They want to see graphs for this. So how do we do the graphs for this? That's the next thing we have to do. Calculating pressure coefficient for smooth and then for turbulent. They've given us an equation for it. Even if you don't understand the derivation, this is all you have to use to work out the answers basically. So for smooth flow, H infinity for mine was this. H infinity, remember what is it? H infinity is the tube 34. And that's what it was showing. Well, it was actually showing something like 10 or something, but remember I converted it to meters, yeah? Okay. H1 is the stagnation pressure 1. So just taking theta equals 20 as an example, my H at theta equals 20 was this. You put that into there, and I got this as my pressure coefficient at that point. And you have to do this for each point. So for each point on Excel, for each of these points on Excel, I used a formula. Well, that formula basically, the one that they gave us. H infinity, that's H infinity as well. That's minus H, what is it? Minus H theta. And this thing right there, that is H1. So do that, then drag it down, and you get everything. You get all of these. Messed it up right there. I'll fix it afterwards. Okay, so after you do that for all of them, then you go to turbulent. You do the same thing for turbulent, which is there. This time is going to be different because for turbulent flow, H infinity was different, H1 was also different, and of course your readings will be different. So that replaces, and that replaces, and then you put in these for each one, and you do that for all of them. After you have done that, you plot those on one graph along with this. So how did I do that? I made another column for this right here, and the formula inside this column is basically 1 minus 4 sine theta squared. So sine squared theta. 1 minus 4 sine squared theta. The reason that is there because Excel likes radians. So you have to make it radians and then put it in. G3 is that right there. These things, my thetas. So since it's sine theta, then the formula just goes through all of the thetas one by one. You can just drag it down after that. So that's how I got that column for their frictionless one. So this is the frictionless one. This one is my turbulent one. And this one is my smooth flow one. And I'm going to plot those on one axis against theta. And it looked like this. That's what I got. Okay? So the next thing after that... Oh, hold on. Let me just say which one's which. This one that you see, that nice smooth one, that's for frictionless. That one that kind of came short and the flow separated early, that's actually flow separation. So behind the cylinder, the flow has separated. For the smooth one, it kind of separated kind of early. And then for this one, the turbulent one, the flow separation was later. And lots of, I don't know, discussion-y stuff that you can write. Next is... Okay. The next thing is estimating the coefficient of drag. So we've done the first two things. We've done that K thing, which was the tunnel calibration constant. We've also plotted a graph with 3 lines on it. Now the last thing they want, as a bare minimum, of course there's lots of other stuff in that guy's example, but the bare minimum stuff, estimate coefficient of drag for both smooth and turbulent. How do you do this? Well, there's another equation given. So that 2-page spread of derivations is really only those 3 equations that you need. This one, the one for plotting those graphs, which is there, and the other one that you need from that sheet is this one, really. You don't really need much else, unless you're doing in your introduction section, unless you're covering the derivation as well, which I haven't decided if I'm doing or not. So the last thing that they want is calculating the coefficient of drag. They've given us an equation. Focus. Okay. They've given us an equation. It's basically the area under this. Pressure coefficient times cos theta. That graph, the area under it halved is CD. So it's going to look something like that when you plot this thing. And integrating means kind of like finding the area, right? So find the area under this, that plus that plus that, half it, and you get your answer. And in the sheet they say that you can use an approximating method like the trapezium rule, or the what's the one they said? The Simpsons rule or something. I don't understand the Simpsons rule, so I might use trapezium rule to just approximate, to estimate the area under this graph. So how I did this on Excel was, it's pretty simple. Let me show you. Right here, so I just added another column of cos theta. To do that, you just, the formula is cos, it is literally simple, cos, and then convert it into radians. A4 is that, so convert these into radians and put them inside a cos function, and that's how you get a cos graph on Excel in the simple way. And then I just did equals that box times that box equals this box, and I got that. And then I just plotted my smooth flows one, and I plotted my turbulent flows one, and it looks like this. And what I'm going to do, inshallah, is using trapezium rule, or if I can understand the Simpsons one, then work out the area under this, including that, this bit, plus that bit, and then half it. Area, and then half it. So that is the result section. They want to see a sample calculation, so something like that basically. That's a sample calculation. And that's it, I guess, inshallah, for the results. The discussion looks long though. May Allah help us.